Hey, Moein, I guess now we are recording. How are you doing?
Yes, I'm doing fine. How are you?
I'm doing fine too. I'm doing fine. All right. So, hi everybody. We're back again after I guess 1 month or 1.5 months. And as usual, a lot has happened in the world of AI, and we have a lot to talk about. Now, for today, Moin has kindly agreed to take the heavy lifting of updating on the majority of the AI news that came out. And I know that there weren't scarce. We had a lot of good models that were released. We had a lot of exciting news that were shared with the public from AI researchers, those commercial AI companies, and different stakeholders in the field. And as far as I have a big exam coming up, so I have been a little bit lazier this time, but I do have two blog posts, or better to say, two different topics that I guess were very informative, and I really didn't want to miss them in between all these regular updates of new models and new tools that we always have. So I'm going to talk about those two, and then Moin is going to kindly take care of the majority of the news and updates that we have had since the last time that we met each other. So Moin, if you want, you go forward, say hi, and if you have any introductory points to share, and then afterwards we can begin.
Yeah, thank you. Yeah, of course, a lot has happened in the last 5, 6 weeks. That's we recorded the last episode, and I think, like always, we will probably skip the most public announcements like Sora 2 or the others that you've probably heard about and read about a lot, and we will just maybe just a little bit introduce the idea of what it was and maybe show some examples. But I don't have anything on these big announcements to dive into because I think everyone these days follows them.
Yeah,
But in my list, I have some other blog posts or and some book recommendations that might be interesting for you. So yeah, stay tuned.
that's great. That's great. Thanks so much. Yeah, I guess we have Sora version 2, which unfortunately I don't have yet the invitation code for that, so I've not yet played with it.
Oh, I can give you one.
Oh,
Yeah.
really? I would appreciate
Yeah.
it. Thank you. I didn't know that you have it. I should ask you for it. Yeah, please. I would love it. And then yeah, that but again, I watched some of the videos and reviews about that. That was very impressive. It's still not perfect. It does make mistakes, but much better in terms of physics and the
Mm,
fidelity to human faces, the fidelity to prompts. Perfect model. Yeah, please share that invitation code with me. I would love
sure.
it.
Definitely.
Awesome. And then the other thing, the other model that came out, maybe just to quickly mention it and then pass, was Cloud 4.5, which again, moved forward the benchmarks for coding and agenting behavior, and people actually relied on it, for very long duration kind of processing tasks. I guess there was a record of 30 hours of consistent thinking and acting and, action taking. So it is becoming more and more agentic, but I guess that is no surprise. As we go forward, these models are getting better and better. So after putting those two models aside, I'm going to start talking about the first topic that I wanted to share with everyone and with you today. And that was a very nice blog post that came out from Thinking Machines. And this was a blog post. Let me share my screen and then go ahead and talk about the details of that. This is a low, and then we want to go and let's see if I can see that. There we go. All right. Are you seeing my screen now? Perfect. Yeah.
Yes.
So
I think it would be more readable if you can just zoom in a little
zooming in a
bit.
little bit. Sure, of course. Let me. Okay. How
Yeah,
about now?
perfect. It looks great.
Perfect. Yeah. So it came up. It came out of Thinking Machines, which, if I'm not wrong, is the startup that one of the previous
Yes.
co-founders of OpenAI has had, Andrew Murati, if I'm not
The CTO, the
wrong.
Murati, I think.
She's the
Yeah.
one. I guess Marathi actually has co-founded this one. But anyhow, I mean, regardless of who has written this is a very enlightening kind of blog post, and it touches upon one of the issues that we always see in the world of large language models, and I believe almost everywhere across deep learning, and that is the point of determinism and non-determinism. And to just give a quick overview of what determinism means, you know, uh, in a nutshell, what we mean by determinism is that we really want to have full control over how random our model generates its outputs. Say, for example, if you have a large language model and if you ask it to give you a poem, for example, you really want to, I mean, naturally, we want to see different poems. If I go to ChatGPT, ask for a poem, I really want to see its creativity every time coming up with a new poem. But it's also very plausible to have the capability of making the model's generations fixed or making it non-random, or as more technical people always put it, deterministic. So that is the meaning of determinism, to make sure that the outputs are not random unless we want them to be random. And for those of you who have been working with large language models, you probably know that we have a parameter in almost every modern large language model that is called temperature. And temperature is basically, I mean, the closest in terms of concept control knob we have for controlling how random a model generations are. And the way that it works is basically by affecting the next token prediction mechanism of this large language model. So I guess this very first figure that they have put on their blog post is very informative. We know that these large language models always look at the prior tokens that they have predicted to predict the next token that will perfectly match the sentence, or at least match the sentence better than the other tokens that they have in their dictionary. Say, for example, if a model has generated the story of thinking machines corporation begins not in A, and then it wants to think of the other token that they should generate after this. And so they look at their entire glossary of vocabulary, I mean, all the tokens that they can generate. And the way that these models usually predict is that they predict the probability of each of those tokens being the best fit for the sentence to the extent that it has been generated so far. And then it gives percentage, it gives different scores to each of those tokens. So for example, here, the word garage might actually be a little bit more likely to fit here, whereas the word boardroom or corporate or lab, they might be a little bit less likely. And we know, as expected, the way that this thing naturally works is that if you set the temperature to 0, the model is going to take the most possible, the most probable token and predict that one as the next token and then move forward with that. But if you increase the temperature, chances are that not always the most probable token is going to be selected. So sometimes the model is going to, for example, take the other likely tokens that could have still come in the sentence, but not the most probable one. And this is how we actually play with the temperature and can have a role in the generation of the large language models. But the point that this blog post is talking about, and I guess something that we all have seen, or at least we can easily demonstrate if we go and work with one of these top tier large language models, is that even if you set the temperature to 0, you still are not going to have a fully deterministic model, meaning that if you set the temperature to 0 on a local large language model, or even on some of these larger commercial ones that let you to play with the temperature, and ask the same question from the model, you still have a chance to see different responses. And this blog post is going to dig into this and understand why this is happening. And of course, you can think of why this is a big deal, because not in use cases like generating poems, which basically doesn't really matter if the model is deterministic. I mean, we even want them to be non-deterministic. But there are certain use cases, such as, for example, medical use cases, right? Or very pinpoint scientific use cases, or even some military use cases, whatever. That these models should be super, super deterministic. We don't want them to generate different output depending on running, depending on which run they are at. And if we run them multiple times, we don't want to see different outputs coming out of their tokens. So they are deep diving into this and see why this happens. And to just cut to the chase, the main etiology, the main cause of this issue is basically lying in the nature of how we represent float point values in programming, and in this specific case, in PyTorch or TensorFlow or whatever framework that we use for coding these large language models. And what they're going to say is that imagine that we have coded something like this, which basically are two different tensors randomly filled out in PyTorch. And imagine that we have set the temperature to 0. So basically, all the time, these tensors should be kind of similar. And then we try to do a math multiplication of these two tensors to each other, and then try to understand if the values of this multiplication is going to be similar or constant every time that we do that operation or not. And spoiler alert, it turns out that it is not always the same value. Now, this might still look like a little bit complicated, so let's scroll down and show it even in a simpler demonstration. So they are talking here about a rule that they called floating point non-associativity. What it means is that if you are just thinking of the mathematical operation sum, which is basically adding a few values to each other or a few tensors to each other, this is the cornerstone of most of the operations that happen in a modern neural network, such as large language models. And what they say is that, unlike what we know from math, that the order of summing a couple of values is not going to change the final output of the operation. This is not the case when we are dealing with computer science like floating numbers. What this means is that this sum is not necessarily equal to this sum, because the order of the operations here are going to be different. In programming, when a kernel sees this expression, it's going to first sum these two values, and it's going to subtract 1e minus 1e20 from that first output that it came up with. Whereas in the second expression, the order is going to change. And what they're going to say is that there is a reason that if you change the order of summing a few tensors or a few values, then the results are going to be different too. And the underlying cause was actually super interesting for me. Now let me try to simplify that for you. And this is a very interesting blog post, so definitely go and read it yourselves. But what they say is that the issue lies in how we actually store float values in memory. And we know that when we talk about float values, we often talk about 32 bits or 16 bits. So this term bit that comes after is basically how we store values in a computer memory. And when we say that we need to store a floating value in 32 bits, it means that we have a limited amount of storage dedicated to a single value. And if your value has some details, has some, a lot of random digits in it that might exceed the capacity available on the computer for storing that value, then those extra digits are going to be kind of cut off, and then your value is not going to be as accurately as you wanted it to be stored on the computer. Now, they try to show this with a simple kind of representation here. They say that imagine that we have basically we want to do this sum here, 1230 and 23.4, and they say that okay, so if we want to store these values in the computer hardware, we really do not store them as their true self like this. We basically change them to float values, and the way that we usually do that is by making them, by expressing them like using some exponents, and then basically moving them to the logarithmic scale and to the exponential scale. So for example, 1230 will be represented as 1.23 times 10 to the power of 3. And 23.4 should be represented like 2.34 multiplied by 10 to the power of 1. And don't forget that we are currently talking about exponential in the base of 10, but when we deal with computers, this is usually in the base of 2. Again, it really doesn't matter, but we can still see the issue even when we are dealing with base of 10 here. So you see that if we sum these two values together, the ultimate value is going to be something like this: 1.2534 times 10 to the power of 3. But imagine that your computer or your programming software or whatever, your kernels, only allow you to save 3 digits as the first value here before multiplying it by whatever exponents. So this basically means that even though you have 5 values here, the last 2 digits, 3 and 4, cannot be stored. So they're going to be cut off. And what is going to be saved on the computer is 1.25 times 10 to the power of 3. So here we actually see how some basically a little bit of precision is going to be lost by only saving a floating value to disk. And that kind of explains why when we sum a few values to each other that are all small values, floating number values like these, the order of the sum matters a lot, because these extra digits are gonna be cut off from the output of those sums. So basically, if we go back here, if you sum these two values together, those extra digits that are gonna be cut off are gonna be different compared to the time that you first subtract these two values from each other. So that kind of explains why experiments like these, basically results in different sort of outputs. So here they basically are, they have come up with 4 different floating values, and they have tried to, shuffle the order of them within this array, and then sum all the values together, basically reduce this entire tensor into one single value for 10,000 times. And they say that, by doing this, we actually get 102 different unique results, meaning that by only summing these 4 values together in different orders, you can have 102 different unique outcomes. So even if you set the temperature to 0, because we are dealing with neural networks, large language models that have many, many operations in their architecture that are based on summing up values, because still there might be issues with in which order the values are going to be summed up with each other. You might see various outcomes. But now the second question comes to mind is that how is it that the same language model with the same inputs is going to have different orders for running some operations, or subtract operations? And the answer to that, as some of you might have guessed, lies in the concept of batching. Because when we are dealing with GPUs, when we are dealing with these large language models, we never feed one single data point, input data point to the models, and wait for one single output. We usually batch millions of requests to each other, and those can come from different users or even from the same user. And then when we have a full batch, we then feed that entire batch to the GPU, and then we use the magic of the GPU where the GPU can basically handle all of these parallel operations at the same time, and then get the output for all of those input data points at the same time. But the thing is, we know that when the GPU is actually processing all those parallel input data points, there are many instances where it needs to do operations on batch, and then it need to reduce the dimensions of the tensors. It needs to add some tensors to each other, and those are the operations that actually will result in this loss of precision when dealing with floating points. So then this paper dives even deeper and talks about what specific batch operations are the cause of these inaccuracy here. And they talk about 3 different issues that happen. And those are interesting ones. And see here, if I can find where they talk about all of those here. Thus, we only need to worry about 3 operations that involve reductions. And reductions is, again, is a mouthful for those batch-wise sum operations: the RMS norm, the matrix multiplication, and the attention. And then they go ahead and explain how each of these batch variant operations actually results in different order of summing values to each other, and at the end of the day results in different outputs. And again, so this might be a little bit too technical for us to deep dive into, even though it's not very difficult to read. I really encourage you to go and just review these operations and understand how things work. But what I really want to point out to at the end is that after they talk about all of these, then they go ahead and propose their own invariant variations or batch invariant, variations of these operations. And they basically put together some RMS norm operations, attention operations, or even matrix multiplication variants that are not reducing the values in the batch dimension. Basically, they are making sure that every sum operation that happens to a single data point is going to remain similar, regardless of the number of the data points within the batch, regardless of the position of a single specific data point in the entire batch, and things like that. So basically, they try to combat basically they try to ensure the order of sum remains constant for every single data point that is entered into the large language model, regardless of where it stands in the batch. And then as expected, they come around and they compare their approach with the state-of-the-art approach. This cuBLAS is actually a library from NVIDIA that takes care of this, all batching and stuff. So they show that the solution that they have come up with is still not that slow. I mean, it's not as fast as what the current state-of-the-art operations are, but it is not as slow either. It is a little bit less optimized for the sake of speed. But on the other hand, it is actually 100% deterministic. So they come around and they talk about some experiments that they did with this model, Quen3, and they say that we basically try to run it for 1,000 times on the same input data, and we realize that there is no divergence, there is no different output when we actually use our own versions of those batch-wise operations compared to the state of the art. So they say that if you really, really want deterministic outputs, you might still need to sacrifice a little bit of the speed of your inference, but at the same time, you might get completely deterministic outputs, which makes a lot of sense because we have a lot of use cases in which actually deterministic answers are far more important than a speedy inference time, because we don't, for example, care if the entire AI application on a single medical image is going to take 10 seconds or 20 seconds or maybe 15 seconds. But if the latter is going to be fully deterministic, resistant to random noise and much easier to debug, why not to just sacrifice 5 seconds and instead have a more reliable model at the end of the day? So very interesting blog post. I personally learned a lot from this. And again, a lot of these things that they put there, they have programming experiments already available that they can go and play with their notebooks, or that you can basically replicate their own code. A very enlightening piece of work.
Yeah, definitely. And it was on my list until I understood that you want to present this. So I waited to just learn from you. And
Thank you.
During your presentation, I was thinking it's really great about you that you can present a long article like this in such a fluent way without even thinking what you wanted to say or what parts are necessary for the audience to understand the next thing. And this is a really great skill that you have. And yeah, it was a definitely informative blog post. I wasn't thinking about this problem in this sense and what was causing it, basically. And knowing that how simple mathematical principles can cause such a thing, and that is understandable, that could be fixed with probably some not very complicated solutions.
Exactly.
It's really interesting, and it shows that just debugging is very based on first principles, is just very doable in machine learning. And I think that is one of the beauties of this field. One thing that came up at the end of this, when you were presenting the part when they overcame this problem, and is this question that these models, do they need retraining with this method, or this is just happening in the inference?
I honestly don't think that they need retraining, and I also didn't read anything about that. I do think that, I mean, the beauty of this blog post is that it means that whatever models that we already have out there, you technically can just come up with a new batch-wise operation, maybe a simple inference package that a place like Hugging Face could have, or even Torch itself can have, and those can basically run the inference on the same large language model. But you, as the user, just need to know that this is going to take a little bit longer than the regular inference, but instead it's going to be 100% deterministic. So I guess it's only a matter of just batching the data, because if you feed single data point to the model, it is not going to make any difference. And obviously, we do know that if we also change the GPUs, things like this can also affect randomness. So assuming that all that we already knew is constant, and you want to still batch your data and run a batch through inference, you just need to make sure that your batching operation is this, basically resistant to changing the order of the sum operations. As far as you do that, everything is going to be the same as before.
Yeah, so the solution looks pretty simple, at least in theory. I'm not sure how in implementation it looks like, but yeah, it's really great that it doesn't require retraining of the core model.
Yeah.
Okay, great, amazing. So
This
if
is
you
your,
agree,
yeah.
yeah, I can move on to the next paper. It's a bit different. It's in vision instead of NLP, and it's not about one of the, I don't know, very hot topic or trends of AI these days, but I found it interesting. So let me share my screen here. Okay. It wants me.
Should I give you any permission to share a screen?
No, it says that because I just allowed it so that Chrome can access my screen recording. I hadn't allowed that before.
Oh, you
It
need
tells
to
me
go
that I
back.
need to quit and reload, and I don't
Yeah.
know what happens after that.
I think that if you
So
just go and come, because I have the recording going on, maybe you can just go out and
yeah,
come back
so
for a
okay,
second. Everything will be,
and
yeah,
hoping that
we'll
everything will
wait
be
for you
fine.
here.
So let me. Okay.
All right, so let's wait for Moein to come back. Welcome back.
Okay, I hope everything looks
That's
fine
all.
here. Yep. Okay.
Awesome.
So share my screen. Okay. Can you see my screen now?
Yes.
Okay. So this is the paper about parameter efficient fine-tuning for medical image analysis.
Hmm.
And before I dive in, and can you see my video at the
Yeah,
same time,
can
or
see.
do I need to move
Yes,
the
yes.
Chrome?
Yep, I guess it's
Because
that.
I can't see you, and
No, but I do see your screen and also your video at the same time.
okay, so I hope it's getting recorded. And if you had any questions or any comments, please let me know because in
You're
voice
not
because I can't see
like,
you. Yeah. Okay.
sure.
So okay, and this was a bit different to me when I read the title, and I wasn't um, kind of like expecting using parameter efficient fine tuning for medical image analysis. I mean, let alone medical image analysis, even for um, imaging itself in vision. I hadn't seen lots of these use cases, but this was the first one in this area using these methods that we use this abbreviation PEFT for parameter efficient fine tuning, which was first introduced in the world of LLMs when they wanted to fine tune them on some smaller data set without tuning all the parameters at the same time. But now it is being used also in computer vision and now also in medical imaging. So they wanted to propose a benchmark of 17 distinct PEFT algorithms, which was shocking to me that we have 17 of them because I had only heard of LoRA by the time.
Yeah.
And they used convolutional and transformer-based networks, and they tried it on image classification and text-to-image generation, which I think is a good start on these sort of benchmarks and research area for the beginning. And they overall did more than 700 experiments, and they found that these parameter efficient fine-tuning algorithms that I will dive into deeper a bit further are particularly helpful in low data regimes, which is common in medical imaging. And they can give you performance gains up to 22% in discriminative and generative tasks.
Mhm.
So this was a pretty much exciting abstract. So let's get to what these methods are and how they did these experiments. I really like these experiment design of this research and how they did the ablation studies. So this was also another a positive thing about this paper that came to my mind. And this is the methods that they investigated in this research. The one that I think we are more familiar with is LoRA,
LoRA. Yeah.
which is low rank adaptation of some of the weights in the model. And here you can see if they are additive or selective. So let's here just get an intro, a very short one on what are these algorithms and how do they help. The problem after introducing and working with these large language models was that, of course, they were very large. They had lots of parameters, billions of parameters. And like before that, we used to fine tune a whole, I don't know, ResNet model on a new data set. This is practically not feasible with these large language models, given the compute regime of that most institutions, academic institutions, have access to. Maybe Google or an OpenAI can fully fine-tune some of their LLMs once in a while, but most of the academic institutions don't have such a computational budget to be able to do so. So there were we had this new line of research from 2022, even 2020, based on this one, that they introduced some shortcuts. We can look at it to adapt a large language model at the time, or any basically deep learning model, with few tweaks to their own weights, and be able to somehow fine tune those weights to a new data set or a new task.
Mhm.
And the most famous one that was really and which was really popular at the time was LoRA, and it allowed for just adding a few weight matrices to the lots of the billions of parameters of the model, and only adapting those weights was kind of enough to adapt an LLM or a model to a new task. And the good thing was that it needed a lot less compute to fine tune such models, and it performed really well. And since then, and more recently, we have new methods available. I haven't studied them in depth, so just we can rely on the summary here, and
Yeah.
also look at this type here, which mentions whether they are additive or selective. By additive, it means that, like what I mentioned for LoRa, this method introduces new parameters, new initialized from scratch parameters to the model weights, and those get adapted to the new task, and the model's own weights are frozen, or at least most of them are frozen. However, in selective, no weights are added, and there is a selection of a subset of the parameters of the model, and those weights are only adapted to the new task. So this could be 1%, 10% of the parameters of the model, and it still saves a lot of compute for the researchers. So this is an important table in this work. explaining what are their methods and their categories. And they also go deeper and provide some more explanation here for these methods. And here are some overall results that we can go through. This figure shows the performance of the two of these methods, the BitFit and LoRA, for the ViT base on this ham data set, which is a not a very huge data set in the order of thousands of images. We will see the exact numbers of images in a table below. And it shows that when we go to fully fine-tuning using 100% of the downstream datasets images, which is exactly the most compute you can throw at the model. You are full fine-tuning, so you are changing all the weights in each update. And when you're using 100% of the dataset, so the model sees all the images. And it's no surprise that, at least for these two tasks, that it's outperforming the other methods. But the promise of the paper and these methods was that in low data regimes, when you only have a few images and you don't want to change all the parameters, maybe these methods can give you an edge. And this is the case for ViT base. And as you see, when you are using only 50% of the downstream data sets, they are all the performance of the green and blue lines, which are for these PEFT methods, are better than fully fine-tuning. So by using less computation, you get better results. And when you go to ViT large, it gets even more interesting. ViT large is a near 1 billion, as far as I remember,
Very
model. Yeah, very lots of parameters. It's much bigger than the base one. And here you can see the difference of different methods. So here, LoRA is much outperforming the BitFit. And as you see here, even to the 80% of the, when using 80% of the images of the dataset, it still gives you an edge. So it's not only for when you have low, very limited numbers of images in the downstream dataset. Even as high as 80% of the downstream images, when you use all of them, and you see that it is still has an edge over the fully fine-tuning. But BitFit is only helpful if you have very limited number of images in your downstream dataset. So it shows that when you go for larger models, the promise of these methods, especially for LoRA, is more pronounced. So this was an interesting plot at the first of this paper, at the beginning of this paper. And the second one is for the generation task. And as you see, by only using 10% of the samples, the models are still able to generate sensible results. Like, for example, this one gives pretty much good results. And however, this one is not really helpful, and it's getting those repetitive patterns, which is expected in fully fine-tuning and when the model gets overfitted to the downstream dataset. So here was just a brief overview of the results. In the next tables, it goes into more depth. And I go over my highlights so that we can just keep on the points that was kind of like a summary of their findings. Okay. As we kind of expect, they found that for the ViT base, and it should be noted that some of the results for the ViT and the ResNet were different. And the cool fact is that some of these methods, not all of them, could also be used on a pretty, we can say, old model like ResNet. And yeah, considering that these are all methods that were probably mostly designed for LLMs by their researchers, but it's interesting that some of them could also be applied to ResNets, and this table shows the results for the ResNet. But just considering this figure 1 that I just mentioned, they said that we find that when using 100% of the available downstream data, full fine-tuning is optimal, closely followed by LoRA. As the availability decreases, however, the benefits from these parameter-efficient fine-tuning methods approaches increase. And the crossover is at 50%, and this was for ViT base, as you remember here. And when all approaches are approximately equal. For smaller data sizes, both these efficient approaches consistently outperform fully fine-tuning. And yeah, LoRA gives you some 6% gains over the baseline. However, for ViT large, the trend is similar, but the crossover now differs between these approaches, and LoRA overtakes the baseline as early as 80%, while BitFit is only better at data volumes below 20%. So as they mention here, the take-home message is that when data are scarce and upstream model is large, it becomes especially important to consider parameter-efficient tuning. And I think this is the gist of this whole paper. And so if you have a very huge model and a very limited number of images or any sort of data in your downstream task, and you want to adapt that huge model that has been trained on probably gigantic pre-training data sets, you probably will have a better time using these methods instead of just going for fully fine-tuning or some shortcuts like linear probing, which doesn't really work well in these scenarios. So and this was some interesting start on this. And then they ask, can these methods improve transfer to discriminative medical tasks? So, and they choose these data sets. These are not very huge data sets. And as you can see in this table, you can see the number of images in them. So this breast US has only 584 images in it, and you can see the rest here. And I think we can only explain it from the table here. Comparing different fine-tuning methods for ImageNet pre-trained ResNet 50. And ResNet 50 is could be considered a very small model. It has only 23 million parameters when fully fine-tuning the whole model. And dataset size and parameter count are indicated in brackets. These are parameter counts. So 23 million when fully fine-tuning. When adding only a linear classifier and freezing the whole weights, it will be around 4,000 to 7,000 parameters. This method uses 10 million parameters, and you can see the rest here. Yeah. The best result for each dataset is highlighted, and the average rank for each fine-tuning method is shown at the bottom. So as you can see from these highlights here, the average rank of this method called SSF is 1.2, which is better than all of the other methods, even fully fine-tuning. So it's interesting that for these data sets, and we cannot, I think, generalize to all data sets, we should consider that these could be considered as medium-sized and low and very small, maybe data sets for fine-tuning. In such data sets, using these efficient fine-tuning methods that only use as low as 60,000 parameters of the model instead of 23 million can give you an edge, and it can improve the performance. Like the average F1 score of 0.77 could be improved to 85%. And I think this is very cool finding, that you are spending less on compute and you're getting much better results. And it is still a ResNet 50, and these methods are very new. And I really didn't expect this. And it was kind of like shocking to me that, okay, why are we fine-tuning these models, having these methods that can just boost the performance and also at the same time reduce the computation we need to throw at these models. So this was a very interesting result here. And you see some of these methods are missing, like LoRA, because LoRA cannot be applied to ResNet 50. And because the way the researchers developed the LoRA and how it worked, the loss function there is designed for the transformers.
Yeah.
And further in the paper, we can see another table for ViT when LoRA is also included. So I think the answer to this question here is yes.
Yes.
And it mentions that the SSF method, despite only training 60,000 parameters, which is 25, which is
0.25.
0.25%, improves performance by up to 22%, which is a really
Insane.
crazy result. Yeah.
The same.
And yeah, the next figure is the performance versus parameter count for ResNet and ViT. So the left side of this figure shows the results of that table in another kind of visualization. Here, the size of the circles show the number of parameters, and as you can see, the fully fine-tuning uses much bigger parameter count than the SSF, and it is lower in F1 score performance. And the right side panel shows the results for ViT, and as you see, it is more cluttered because more methods are applicable to ViTs. And here, LoRA outperforms even SSF, which is cool. But it's interesting that SSF is still a good method and it's very close to LoRA, and it uses pretty, I think, significantly lower number of parameters even than LoRA, let alone the fully fine-tuning. So again, it shows that not only it reduces the computation needed, it can improve the performance of the model on the downstream task. And yeah, we also see that the benefits of PEFT increase slightly as the model size increases, with a 4% improvement for ViT base going to 6% for ViT huge. And the good news is exactly this. The gains of these methods increase when the models get even larger than your baseline. So it could be a good news that we can probably use some of these huge medical models or vision models like SAM, MedSAM, all of these, and fine-tune them with these methods to a limited downstream data set and hope that it can use its the good performance of the pre-trained model. So these are the methods that outperform the others. And then finally, it also looks into text-to-image generation, which is another cool task, which is really kind of a hype at these days. And we can see lots of models being released for image generation from radiology reports and etc. And again, similar results could be seen here. And the metric here is the FID scores. So it's not a perfect metric, but it is one of those good quantitative metrics, because most of the time the results of these generative AI models are evaluated visually by experts or by just readers of the papers. But one of the good quantitative metrics that could be used is this FIT score. And again, a similar table is provided here. And here, the results is even more interesting. And as you see, the best rank is for when only the bias terms of the model are adapted. So no new parameter efficient fine-tuning method like LoRA, no fancy terms, just when using a stable diffusion and only fine-tuning the bias terms in the unit, it gives you the best results, which is crazy. And the other methods, I think the second place would be this one, SVDiff, which is a very sophisticated method developed only for diffusion models. It places second here, very close to just fine-tuning the bias terms. However, the performances are very close. So maybe just sticking with this simpler one that would suffice.
And interesting,
And
very poor performance here.
yeah, Yeah, and the other methods also do not work very well. And they mentioned that the LoRA, the best performing method for classification tasks, fails to provide any
Yeah,
benefits in image generation. And you can see here that the
yeah,
results
fight is
don't
not
look
very
too
high.
good. Yeah. So simple strategies such as fine-tuning just the bias or normalization layers are amongst the best performance, assuming first and third ranks respectively. And yeah, this was it, and I really was excited about this paper, and it's really m- was unexpected for me to see uh, these methods being used in this area and with such good results. But yeah, I would be really happy to know
Yeah,
what you think about it.
I totally agree. This was a crazy paper. I guess there were 2 points in this paper that really caught my attention. First was applying these techniques to the domain of computer vision, because as you said, we were mostly used to see LoRA and other adapter or PEF techniques like those in the world of large language models and text prediction. Now, bringing those to vision itself was kind of very innovative. But going one step further and applying that to convolutional neural networks and even old models such as ResNet was another key, uh, you know, key insight of this paper, that we probably have been fine-tuning these models very inefficiently for the past years, because we always wanted to fine-tune the entire parameters. I remember that we actually had some discussions like maybe only fine-tuning the last layers, or just the penultimate layer, or maybe 2 layers afterwards. But and yeah, we somehow saw those very naive, simple techniques work better than fine tuning the entire model. But I believe now bringing these very sophisticated, parameter efficient fine tuning methods from the world of large language models to the world of vision can actually improve the performance significantly. So I would say this is great. The only question I have for you is that, I mean, have they introduced any practical ways for applying these methods to, say, for example, a simple convolutional neural network like CompNext or FissionNet or whatever that you can basically get from Teams or other Python libraries? I mean, if you want to do this practically, do you need to re-implement all these methods for convolutional neural networks or even for ViT and other stuff? Or are there already implemented solutions?
Uh, they provide some code snippets in their appendix that I think could be just
Use
used
that's brilliant.
in probably any model. I'm not sure, but at the end of this paper, let me share once more. Um, they provided snippets for each of these methods that could probably be applied to the models, as you can see here.
Oh
Training
yeah,
protocols for selective PFT methods, for discriminative tasks, and for CNNs specifically. If you want to go with this method, you add these probably. And yeah, as you see, it checks for the modules if they are a certain kind, and they apply some modifications on that.
I
And I think they
understand.
provide, yeah, for the TSA, again, they do the same thing. So I think it
Very easy.
it could be used in everyday model training without probably many headaches, but um, it would be great to see some, um, I don't know, maybe kind of a GitHub repository or some add-ons, some extensions to Teams or Hugging Face, where you can simply apply these methods to the
Agreed.
models that you.
Agreed. No, but this is super useful and super practical, I believe. I mean, it can significantly improve the performance of specifically medical models, given how usually smaller data sets are. So yeah, very interesting paper. Thanks for introducing. I mean, this is one of those papers that you usually want to jump into code and play with that a little bit and see what comes up.
Yeah, definitely. Yeah, and one of the challenges we were facing was with fine-tuning a stable diffusion for a limited, unlimited data set to generate some CT scans. And I think this would be a good idea to just try and see how it works on this task. And yeah, it seems like it should be easy to apply it to a ViT or a unit, for example.
Yeah. No, I guess this is interesting, and
Okay.
this will probably be added to the kind of experiments that every single model should have prior to public release or public use or whatever. You need to see if using these adapters are going to improve the performance of your model or not. But this is super crazy. Thanks for letting us know.
Yeah, yeah, my pleasure. And also one thing about the kind of the design of this paper, it's this sort of research design that you apply a few methods on a few data sets, on a few model architectures. I think this is a very safe way of producing very useful results and being sure that your paper is adding to the literature,
Yes.
and without being worried about whether these methods works or not. Is this a good question that I'm asking? Because when you do such a research, and when you select such a huge list of methods and apply them to very different models, and you care to choose two different architectures so that it makes sense to the reader that maybe this method could have different results on the transformer, and you have answers for that. This is, I think, a very good strategy for having good papers. I'm not sure how you think about it, but I had a similar experience in that, when we benchmarked some contrastively
Mhm.
pre-trained models and applied transfer learning to see how they perform on some downstream tasks in medicine and different domains. And just by comparing the results of their downstream models, we had a good paper, and it could be
Yeah.
published on some good venues. But I'm not sure if this strategy is going to work from now on, or is it getting, I don't know, old-fashioned or something? What do you think about it?
No, I do think that it is gonna work. I mean, to be honest with you, I guess every single paper, every single research strategy is going to work as far as you have a clear problem and you have a well understandable motivation to do so. So the problem that these people have started with when doing this paper was actually super logical and something that was a huge pain point for most of the deep learning researchers in medicine, because we often have small data sets, and we have been wrestling with this issue of how to best fine tune a model for years. So if you have simple solutions to offer to long standing problems, why not? I mean, uh, again, the prior blog post that we talked about, that also didn't look that much sophisticated, to be honest with you. I mean, everybody talked about this non-determinism issue, and then someone comes out and say that, okay, let's not look very complicated to the problem. I mean, let's keep things simple. Maybe there are other issues going on, because I could also argue that, wow, the temperature parameter is not enough. Maybe we need to add a second and third temperature and make things over sophisticated. But then, you just need to take a moment, look at what is happening behind the scenes, and you probably will understand what is going on. And I guess there are still a lot of rooms for these innovative papers like the one that you introduced. And it is also going to be even more valuable nowadays to produce this kind of work, because when we have this much of hype about what LLMs can do, what agents can do, when you see that somehow most of the publications that are coming out nowadays are kind of clustered around certain niches of literature, like multi-agent, and then LLM, and then inference speed, training, RLHF, RLVR. I guess hopefully I said that right. And you see that there are a lot of areas that have remained relatively sparse in the literature, and nobody is caring about them anymore. Whereas if you just put a little bit of effort there, you are going to see much, much more impact compared to those incremental benefits that these endless, complicated research data on the already explored topics are going to add to us. So I would definitely agree. No, I guess this is a very good example of those papers that can be super impactful without adding complexity to the stuff.
Yeah, exactly. So thank you for
Yeah.
yeah, explaining on this. And
You.
I think we can move to the next topic here, if you agree.
Yeah. Cool.
And the next topic on my list is this one, let me share my window this time, not leaving Chrome. Okay, I think you should be able to see this.
Yes.
Okay, this was a blog post based on a survey that they did themselves, and also another study that I'm going to just present very quickly after this, or middle of this. And this is asking, is there a vibe shift happening? And the title says, senior developers ship nearly 2.5 times more AI code than junior counterparts, which was interesting to just get it started on the blog post. And I'm mostly going over the figures because I think it's a good summary of their findings. As you see, the senior developers who reported that over 50% of their daily coding is by AI is much more than the junior developers. So it could also be expected, but I think the otherwise, the exact opposite of this could also be expected by some others, because everyone thinks that, okay, newcomers are coming to coding, and they just get started with these LLMs, and they say, okay, do this and do that, and they copy paste, and so most of their code should be AI generated. But the fact is, no, these senior developers are using more of these tools in their daily codings. However, it could also be explained in this way, that probably they know what they are doing and they are using
Yes.
it in the right way, and or maybe that they prefer to do a very mundane task using these LLMs and not just to start from scratch coding it, while a junior developer could be fine doing it. And yeah, so these are just some food for thoughts, and the blog post also provides some kind of like these guesses of probably what is happening behind the scene, but no one actually knows, and this needs further studies. The second one is that the perception versus reality of whether these AI tools are really helping. And the question is, how often do you spend extra time fixing AI code? And 65% of people report that frequently. So um, as we have first-hand experience with these tools, we know that probably not all the first-time code suggestions are working well in daily tasks, in the daily coding, and we probably need to do lots of checks and edits to it to make it work. And here it goes to a very interesting RCT, and here is it in my next tab here, if it goes to it. And the title is Measuring the Impact of Early 2025 AI on Experienced Open Source Developer Productivity. And the interesting finding is that, surprisingly, we find that when developers use AI tools, and these are open source developers and they're experienced, they're not juniors, they take 19% longer than without AI, making them slower. So the general perception that these tools are helping to do more, to be more productive, maybe this is not true, at least at this moment. And there are other evidence suggesting the same results. And this is another cool figure. Here at the left part of this figure, you can see the forecasts of the economics experts, the ML experts, the developers, the exact developers here during this study and after this study, of how AI is helping in terms of their speed up. Is it saving time? Is it doing just are they better off without it? And most of the forecasts are like, yeah, it should be helping, it should be saving times, but the reality is the exact contrast. And here you can see the 19% drop in time efficiency, the slowdown that it caused. So they say that this disconnect may come down to psychology. AI coding often feels smooth. Code autocompletes within a few keystrokes. So maybe this effect that you are seeing a huge bunch of text, which is code here, generated and copy pasted into your code, maybe it gives you the sense that you are making progress. But the time you need to put to it to make it work, to integrate it fully with your own coding style, maybe that's just blows off every time saving that you had copy pasting that code. And it was the most striking kind of result from this survey to me. And also that study also was not expected. And in my experience, I was thinking I'm getting more efficient, I'm getting more productive with these tools, but the evidence is suggesting otherwise. And the other figures here, how AI tools affected your enjoyment of work. Most of people have found that these tools make it more enjoyable. So maybe the good side of these tools is that, okay, they maybe are slowing you down, but at least they are making this mundane task of coding more enjoyable to you, or bring back the joy of it when you were first starting it. And yeah, it goes to the methodology and some of the environmental impacts. Yeah.
One thing to mention here is that I do believe that with this vibe coding, we have a lot of what I kind of call illusion of perception. That when we are using them, we feel like that we have fun. We feel like that we are surprised by how good they are. But when it comes to really measuring how much benefit they added to the workflow, then we might be surprised that actually they are taking more time. And I kind of resonate with this finding because I have found myself, I mean, there are two ways that you can use this thing. You can use them in a way that people usually refer to as agentic way. You basically just give them a task and, maybe at the most just define some rules and boundaries for them and then let them to go and code on their own. And you can come up with a very interesting, astonishing look output at the end, say, for example, a web page, an application, or whatever that is working here and there. And maybe there are some nuances or some glitches there that are not still perfect, but they're working fine. And then you feel like that you're so happy about it. The other approach is that you basically micromanage these AI tools or use them for very small pieces of work that you need to be done. But they are still very clear in your mind that where this specific part is going to fit in and what is the benefit of it and what is the big picture, where in the big picture I am right now, and how specifically I'm using this model to help me. I would say that I more fall in the camp of people who actually prefer the latter approach, because the first approach is interesting, it's fun, it's usually good for not too large of a project. I mean, usually a small scale project, and even those small scale projects that they still do not need, are not intended for high spec applications, do not need constant monitoring and debugging, and you just want to have some fun with your coding, show something to someone and be done with it. Yeah, Cloud Code, whatever tools coming out of ChatGPT, OpenAI, Cloud, wherever, they're great. But if it really comes into putting together something that is commercially viable and then later on you can use it in the long run, then you really need to know what is going on, because these models add a lot of unknown biases and make a lot of unknown decisions behind the scenes without even letting you know of that. They just take it as granted that, hey, this is the way that it should work. And maybe the way that they think the code should work is not going to match the way that the rest of your code has been established. And the chaos actually happens when you are developing an entire system with these models, and in each inference you basically task your model to come up with a feature, and it comes up with that feature, and apparently things work fine. But behind the scene, in every single inference, every of those features has actually had some different mentality of the large system in mind, that when it comes together, neither of these could match and could work aligned well with each other. I've seen that a lot, and I've come into conclusion that if you really want to use these tools, first of all, you should need to understand the big picture of your code. You need to understand the exact pieces that are gonna be together. I mean, these tools are great if you just go to them and ask them, hey, I want to approach this problem. Give me the system. How should this entire thing be built? What is the system design for that? How should I handle the data? How should I handle the code? How should I handle the servers? How should I handle, I don't know, maybe the transfer of the data, the storage of large files I have? They can give you a lot of good insights, but then it is you that need to make a decision. When you make that decision, now you need to jump into every single component and ask it to develop with very clear boundaries. And then when they develop something, you might actually go there and try to read it from scratch and understand how things have worked. And obviously, this is going to take longer time. I mean, obviously, this is going to end up being much tedious than you go there and code everything yourself. So my understanding is that if I know the system that I want to code, if I already have the knowledge of it, I usually start the coding myself, at least write the fundamentals using those code completions that, they just make this faster. They are not going to code instead of you. But then I just ask the AI to fill in the blanks, and I know what it is doing. If I don't know something, if I'm coding something completely new to me, then I will definitely ask AI to give me insights. I will definitely ask AI to develop things for me step by step, but I will then go and study that code myself. This will probably take 20 times more of the time that I could put if I knew how to code that program. But this is my way of learning in the new era, rather than just going and open Udemy and Coursera and learn something from scratch. I learn it from these AI models while doing the project I like, but it certainly is less efficient.
Yeah, and I think this was also a good explanation of what was that 19% increase in their time could be related to. Maybe there are more learning things, these
Yeah,
using these suggestions, AI suggestions,
yeah,
and maybe we see that the improvement of their skills after using these tools are better when they were left alone to just learn from courses. But yeah, I totally agree that just vibe coding and letting the AI take care of everything is probably good for just some fun projects at the weekend, and then to throw them away in the trash. And if you want to build a scalable and build something that could be deployed in real world and work and make some value, it's probably not something that you automate the whole thing with AI. You probably need a good design for it, and you probably want to only generate some code only for defined and deterministic tasks, and not um, unleash the AI and let it do everything from scratch.
exactly.
I totally agree, and I think we can see probably more and more evidence on how best these tools could be integrated into workflows and into workspace to guarantee kind of like the boost in productivity and not the slowdown we see from these RCTs.
Cool. Agreed.
Yeah. So if you agree, you can take the lead and present whatever is next on your line, and then I can take it. I also need to drink some water, and I will come back if that's fine.
Yeah, sure. Go, man. And I
Okay.
will share the
So,
screen while you're doing that. All right. So let's.
okay, I'm back.
Awesome. Are you seeing my screen?
Yes.
Perfect. So this second paper that I want to talk about, this is going to be a little bit shorter discussion compared to the other one. And unfortunately, this paper doesn't have too many figures, and it's a little bit math heavy. So I try to condense the main insight that it wants to convey. But again, it's kind of a nice paper if you are interested in this concept of hallucination. The paper came out very recently, almost a month ago, from OpenAI, and they talked about model hallucination. Now, obviously, all of you know what hallucination is, and we do also know that these hallucinations got much, much better as we went forward. And in the beginning of LLM era, we had some crazy stories of these chatbots falsifying the references and basically confidently lying to the user, or making things up, things like that. And it is still the case in some situations with some of these chatbots, specifically those smaller large language models that are not very powerful. Or if you're asking them something that is really new to them, you might still see some hallucinations. So the problem is not yet fully solved. But I guess we can all agree that it is not better. But this paper is offering some insights on why this problem is not solved 100%. I mean, what is going wrong that after generations and generations of large language models, we still are in danger of or at risk of seeing hallucinated responses coming out of even the best models that are out there. Now, the way that they talk about it, and again, I don't want to deep dive into the text of this paper right now, because I guess it's a little bit, again, beyond the scope of how usually technical we get into this podcast. But I think they talk about a few interesting insights. The first one is that regardless of, regardless of what you do and what can any engineer in the world of LLMs do, uh, the baseline, the base large language model, which is actually the next token predictor version of the models before any post-processing, they inevitably are going to have some hallucinations in their outputs, okay? And they say that, there is basically a lot, I mean, there are a few reasons, a few very important reasons for that. And part of that comes back to the data that we usually train these models on. So they say that, uh, what we usually refer to as epistemic uncertainty, which means that there is some uncertainty in the nature of the data that we usually pre-train these large language models on. And imagine that by this data, we mean most of the data on the internet after some curation. And we really want the large language model to be trained to predict the next token, or to simplify the next word that comes into a sentence. And we do know that not all information available on the internet are fully certain or fully accurate. They are not like that. So these models basically are trained to predict by kind of learning the vibe of the sentence that they're completing. And yeah, they also learn some clear-cut facts that maybe have been repeated many times in their pre-training data. But when it comes into points that are not that common knowledge, that are not that frequently cited in the literature, in data available over the internet, well, the model just see them maybe once or twice, and who knows, maybe when it comes to inference, the model might not remember those facts that it has not seen that often in the training data, and then tries to come up with something that is still, feels the same in terms of vibe, that it still feels kind of appropriate, but it is not in fact appropriate. So they refer to this as epistemic uncertainty, this kind of uncertainty that roots back in the training data for these large language models. And as far as this epistemic uncertainty, we as developers cannot do anything about it. So we can kind of always expect some sort of hallucination in the baseline model. And they also go and talk about other factors. Say, for example, poor model definitions. I guess there was once a discussion on the DeepSeek models that they couldn't basically count the number of letter D coming in the word DeepSeek. And things like this, and where one model excels, the other model has a poor performance. These things, if it is not a universal error that we see across all large language models, these are usually related to the architecture or the training regime or whatever design choices that the developers have had. So even if we had the perfect training data on the board, we still could see some hallucinations because we do not have the perfect LLM architecture at the moment. And yes, our architectures are getting better and better. The community is evolving, the science is evolving, that's for sure. But again, we are far from perfect. And because of that, we can also expect some sort of errors going on there. So let's also talk about some other, maybe a little bit less important factors, such as computational hardness, that sometimes we need to run algorithms on hardware that is less powerful, less optimized for harnessing the full power of these large language models. So we inevitably need to deal with some inaccuracies because of all those suboptimal, sacrifice that we have made. Say, for example, bridging back to our prior discussion, if your model has been trained on float 32-bit float values, and it can theoretically work with those values, but now you are running it on a system that is weaker and only lets you to work with 16-bit float values. So you basically are sacrificing some accuracy there, which might show itself in the form of hallucinations. And then we do have distribution shift. Say, for example, some data that you had in your pre-training corpus and you train your model on are no longer valid, or maybe the features of that data has changed. Maybe the answers to prior old questions have changed. So things like that could also result in hallucinations. And this mostly is the reason behind why we still are in need of approaches like RAG and all its variations. And then GIGO, which I didn't know about prior to this paper, which is garbage in, garbage out. Meaning, if you basically give very poor quality training data to the model, you will see poor quality outputs. Or even during inference, if you ask a question that is very poorly formed, there is a chance that you might also see an answer that is not the one that you were looking for. But all of that I just said, these researchers, the authors of the current paper, are taking as grant. They're saying that, all right, I agree with that. Everything is okay. We do know that all these downsides exist there, and we probably cannot do anything about it in the base model. The base model is going to come out probably with some hallucinations, out of the box. The question is, why can't we control these hallucinations during the post-training phase? Because that is the main control knob that we have over these models, and we try to align them. We try to apply reinforcement learning to them. We try to fine-tune them. We try to do whatever tricks that we have upon our sleeves to make sure that these are the least dangerous, most beneficial models that come to the market. But we still see hallucinations, even in those post-trained models. Now, they try to focus on this area, and then they talk about the main reason behind that. That, to simplify it, what they say is that, the reason is the way that we are evaluating these models, or the reason that we are, basically incentivizing these models during post-training. So most of us know that one important step in post-training of this model is fine-tuning. I mean, fine-tuning could be like regular fine-tuning or with reinforcement learning. And in this kind of step, we usually, again, and let the model encounter some more real-world kind of use cases, and then try to penalize the model if the answers that it is generating for us are far from what we expected them to be. But the problem is here. We always give the model incentives when it generates appropriate answers for us. But we usually do not penalize it when it basically generates answers for us that are wrong. Meaning, if I'm a large language model, I would always have a chance. Say I'm a large language model and you are asking me to answer a multiple choice question for you. And there is only one correct answer among all the choices that you have given me. So I will always benefit from guessing which choice or which option is correct, even though I do not exactly know what is the correct answer. Say I have no ideas about, Moein goes to a large language model and asks about his own birthday, maybe because Moein's birthday is not already on the internet, or maybe it is not frequently repeated on the internet. The model doesn't know about that. So the model knows that, the model thinks that, okay, I don't know anything about it, but if there are 4 choices there, I still have 25% of winning and receiving the reward if I just go ahead and make a guess. So instead of saying, I don't know, instead of saying, I don't have the answer, it is basically incentivized to randomly say something. That is how reinforcement learning at the current state is pushing the large language models during post-training to either the answer and you're giving me the answer. If you don't know it, at least guess, because there is a chance that you might be right. And we are not penalizing the model for blind guessing, because neither of these evaluation benchmarks, neither of these post-training data sets that are out there have actually done that in the past. And it is no surprise. This reason doesn't look like to be that much illogical, doesn't look like to be that out of mind. when you look at it retrospectively, it makes a lot of sense. But I guess neither of us, or neither of those people who actually train these models, uh, maybe cared that much about it to come up with a solution that makes this post-training a little bit more uncertainty resistant. And what the authors of this paper are now suggesting that we should do from now on is that we should kind of penalize the model for blind guessing the answers to the questions it has no clues about. Maybe imagine that in the same multiple choice question, you could say that, hey, the correct answer has 5 positive points. The I don't know answer has no positive and no negative points. But if you give me the wrong answer, it is going to have -5 points for you. So basically, you are changing your reward model. And now you are making it in a way to force the model to only answer your questions, to only generate outputs when it is confident that the output is going to be true. Again, there might be a chance that it is just, it has learned something wrong. Maybe it is giving you some wrong outputs. Maybe it is confident that it is saying something, but it is wrong. But at least it is not forced to blind guess, because it feels like that I'm not going to lose anything if I just say something wrong. This is the entire idea of this paper. They are saying that let's work on post-processing, let's make better evaluation benchmarks, let's penalize the models for not saying I don't know, and see what comes out of it. And then they go ahead, they run some experiments, they offer some insights that are, again, something for you to read on your spare time. But this might be something that we are going to hear more about as we go forward with the next generations of these large language models. Hopefully, the post-training is going to help us a lot for staying away from hallucinations by simply incentivizing the model to say, I don't know, when it doesn't know the answers.
Thank you again for taking us through this very important paper coming out of OpenAI. I had it on my list, but I didn't find the time to go through it, and I think now I have a good understanding of the main ideas there. Yeah, I think again, like what we talked about in the first paper you introduced, when you look at this from the first principles, it makes sense the behavior of these models. And this reminds me of another paper that I don't remember the title to just share the screen, but the idea there was to evaluate if the models if these LLMs are robust to some changes in the benchmarks that they are usually evaluated on. And the authors did something very simple but interesting. They went through some of these multiple choice questions that are usually used in lots of benchmarks to evaluate these models, and they replaced the correct answer with none of the above. So none of the above will be the new correct answer, because the 3 other answers will be false. And they also check this with an expert panel so that the other answers, the other options are actually wrong. They are not kind of like a little bit right. And when you replace these correct option with the none of the above, they make sure that this new option is the correct one. And they found that the performance of these LLMs just dropped drastically, like 34% kind of like drop in the performance, which again, I think is connected to this one. These models are not trained to say, I don't know. They are not trained to pick the option that none of these things is the answer. They have all been trained on lots of examples of seeing the correct answer. And these sorts of examples are probably the outliers, and they are trained to ignore those cases and to always have an answer. And this shows itself in the way that they answer, in the way that they behave in the conversations. They always seems to know everything about everything. And yeah, I think this was a really good change. I think we are seeing more of I don't knows in the GPT-5 version, but the previous versions were just like they could explain about everything they had no clue about.
Exactly. I guess they have applied part of this technique to post-training of GPT-5, because I've also seen it personally that it sometimes tells me that I don't know the answer. And at the same time, people are also reporting more of kind of reasonable uncertainty the models outputs. So I would say that, yeah, this is something that probably OpenAI has already experimented with on GPT-5, and hopefully other models will start doing that too, because we don't want hallucinated models as much as we can.
Yeah, definitely. So I have a few other items in my list, and they are just quick mentions, probably the title, so that the audience could just dive deeper into after this session. And I quickly share my screen. The
Sure.
first two are on GPUs, and these are a bit technical. This interesting, I don't know what to call it, online book or tutorial has 12 parts, and the last part, and this is a book by Google developers, and the first and initial chapters are on TPUs, on transformers, on training, even Llama, which is from Meta, but they have also some sections going through that, and they also have a section in introducing Jackson, how to work with it. But this last one was, I think, one of the most interesting ones, because it's takes you through the architecture of the GPU and explaining some of the most complicated topics on this architecture of GPU thing that you see everywhere, and it's uh, explained very difficult in most other tutorials, but here it's much more approachable. And as you can see, it starts with what is a GPU in the first place, and it goes through the hardware, why we need it, and how it helps to boost the performance of the tasks that you wanted to do and what CPU cannot do. And it goes through the networking, how to connect different GPUs together, and what are the methods that one model could be distributed, the data could be distributed, and all of that. And also it compares its architecture with the TPU, which is another interesting topic that I've always been interested in, but had no idea about. So I think this is a very interesting uh, tutorial and resource to just go through probably every section of it.
Awesome.
And yeah, this was one, and the other is a complementary to this, and this is called GPU Glossary by Model, which is a software that provides kind of like online GPUs that you can use in your code very easily without setting up a new machine every time. I'm not sure if you're seeing this tab as well.
Uh,
I
I'm just
quickly
seeing.
yeah,
Okay,
now
yeah.
now you're seeing this. This is the other one, and again, it takes you through some of the most complicated topics in this area, and this is more technical than the other one, but it is written by a very expert team of who provide GPUs to lots of developers, so they probably know about the hard cases and the errors that you might get when installing CUDA or anything else. And I had these two on my list. The other is a blog post where some books are recommended. And okay, so let me share this as well. And I think I will be done after this, and I will leave it to you to wrap the meeting up. Uh, this is this blog post.
Oh, okay, cool.
The a developer in Germany who works on distributed systems in machine learning, and she introduces lots of books in different categories. It starts from here, I think. Yeah, the mathematical foundations. There are two book recommendations here. This one is a great one, Machine Learning with PyTorch and Scikit-learn by Sebastian Rashka. And it is a good choice because it is with PyTorch,
Mhm.
and most of the other books that I personally started with were using TensorFlow, which later on I put it aside because it wasn't um, easy to learn, and it had its
A new
own
book,
kind of.
right, Moein? I have not seen this before. Is this a new book?
No, I think it is updated, but the main version is, I think it was out at the same time when the other popular book called
TensorFlow.
Hands-on Machine
Yeah,
Learning with
because I
TensorFlow.
can
Yeah,
see, and I never saw this book. I'm kind of regretting that I should have started with this one instead, because we never coded with TensorFlow, to be honest, for the past couple of years. So
exactly. And I think this is a good replacement for those books who are using, which are using TensorFlow in their examples. But yeah, I had also missed this book when I was learning PyTorch or any of these frameworks. But I think for those who want to get started, I think PyTorch is much a better choice to get started with than any of the other frameworks out there. Maybe Jax is another alternative. I'm not sure, but yeah, PyTorch is by far the most um, popular framework in the papers we see every day. And it goes to programming foundations. So if you want to get better at Python, this Fluent Python book, which I have studied a few chapters from, it is a huge book, and
mm,
probably no one goes through it chapter by chapter. It's like a dictionary so that you can just go check whatever chapters you need at a time. And this is another very interesting book, Practical Statistics for Data Scientists. It's written in both Python and R. And I remember it had very simple examples that really made some uh, complicated topics very transparent to you very easily, and there were code snippets all over it. And I think this is a great choice for those who want to be a data scientist and do lots of statistical analysis on large data sets of I don't know, like tabular data sets. And this is not a deep learning book, by the way. I think there was some um, deep learning examples, but most of the book was on traditional machine learning works. And this book on NLP, this specifically, I haven't read that, but it was suggested here, and it seems like it is a mix of traditional and also modern approaches in NLP. However, the next one, NLP with transformers, which is by Thomas Wolfe and other authors from the Hugging Face, is a very great choice if you want to get started with LLMs and the RAG pipelines and everything else that is trend and hype in these days.
yeah,
I think this is a very good place to get started, and it uses most of the tools and modules from the Hugging Face, so you can use the accelerator kind of module to train your models, and you don't need to worry about writing a whole training loop from scratch. So I think this is a very like contained book. You can get started with it and get more and more and learn more and more about how these new models are being used and deployed in practice. The other books are also very good choices. The Designing Machine Learning Systems by Chip Huyen, again, a very popular book. And the newer book, I think it was called AI Engineering. Yeah, AI Engineering by the same author is also a very great and I think a bestseller book in machine learning.
yeah,
And yeah, you can go through all the book recommendations here. The good thing is that it comes from her hands-on experience and real life challenges that she had gone through over the years. And I really like these sorts of blog posts that are a reflection of what the challenges were and what inspired the person to go and read that book and how the books really helped them out. So, and it's better than those sponsored kind of like blog posts that just promote some books. And yeah, I just wanted to share this one, and the links will be in the captions of this video. So yeah, feel
Moein,
free to.
amazing. I like these book introductions, and this list that you shared. I was just scrolling some of the books and trying to understand what this is in there. This is a great list. This is a very nice walkthrough for anyone who wants to get good at deep learning. I mean, definitely me included. I need to learn a lot more about the fundamentals of data engineering, and also when it comes to modern transformers, how these models work, how the different pieces connect to each other. I guess this is great. I guess this is great. Thanks so much for introducing. I also have a fun fact for you. So I wasn't on Substack before you actually showed me this post, and then I actually registered for Substack. And yes, last night I was just playing a little bit with Substack as well, and I find out that there are a lot of. I mean, it was actually more beneficial than X or Twitter for me. I found
Mhm.
much more to the point data there, and it was kind of interesting. I said that this is something that I never tried. I was kind of used to my regular social networks such as LinkedIn and X, and then this Substack looks like to be a very new and powerful competitor. Do you use it for deep learning updates regularly? I mean, how do you use Substack?
I haven't used it for writing tutorials like I did before using Medium, and I think it's best seen as probably a replacement of Medium these days.
Okay,
Most of people are now doing their blogging using Substack, and I think the posts there are just much more high quality than the posts on Twitter or X,
I
and
see.
it makes sense because you need to format it and make it look nice. And the other blog post that I follow on Substack is the one for Eric Topol's,
Yeah,
and he posts regularly, I think
that-
bi-weekly in there, and yeah, those are also good reads too.
awesome, awesome. Thanks so much. Thanks so much for introducing this list and also all the other interesting papers and blog posts that you introduced today. All great. I'm very much sad that I still have 2 more weeks of study. So hopefully afterwards I will jump on all these resources and try to catch up with them as fast as I can. Uh, yeah. So if you don't
Yeah,
have anything
definitely.
more to share, I also talked about the 2 articles that I wanted to share. So I guess if you agree, we can wrap up this session. Again, we deliberately skip the hot topic new models that come out every 1 month, because if we want to cover them, then we need to spend this entire 1.5 hours just talking about what model bet the other model, or how Sora is good or Sora is bad. I guess everybody hears about those topics elsewhere, so we try to cover a little bit more less talked about stuff, specifically when they face medical world and can actually have an impact on medical words. So thanks so much for introducing these topics, Moin, and thanks everybody who listened to us. And if you have anything to
My
say,
pleasure. Yeah.
let's do so.
No, just thank you, and thank you for the deep dives into those two very good papers and blog posts from the last weeks. It was very informative and information dense. So thank you. And yeah, I think I also need to put some time after this to go through those papers and just read them for myself and learn more. Thank you.
Yeah, of course, of course. My pleasure. Thank you everyone for watching us, for listening to us, and hope to see you soon, maybe the next month. Goodbye. Goodbye, Moin.
Goodbye.
Goodbye.
Goodbye, Priya.